Alright, welcome back to Organic Chemistry. This is the fourth in our four-part presentation on nuclear magnetic resonance spectroscopy. In the first section we learned about the basics of spectroscopy and of carbon-13 NMR. In the second section we saw how we could start with the carbon-13 spectrum and interpret it to figure out the structure of the molecule. In the third section we looked at the basics of proton NMR. That is, we saw how that was similar and different from carbon-13 NMR and how molecules can give rise to proton spectra. If you have not seen those different presentations, I would suggest going back and doing so. But here we're going to do a couple of practice problems. We're going to see how we can solve proton NMR. Again, last time we noted that there are three sorts of things in proton NMR that are information-bearing. That is chemical shift. The hydrogen bonding environment, different bonding environments will lead to different arrangements of electrons, which will lead to different energies for this whole excitation-relaxation process, which means that these different environments will lead to different signals along the x-axis. Well, where those come along the x-axis is going to tell us about the molecule. It's going to tell us that those hydrogens are attached to sp2 or sp3 hybridized carbons. It'll tell us if there's strongly electronegative elements nearby. It'll tell us if they're attached to alkenes or aromatics, a variety of things. I don't want you to memorize a bunch of numbers. Instead, I'd sort of like you to understand the different regions of the periodic table, the different regions of the spectrum and the trends within those regions. Integration, the relative sizes of the peaks. Now this is not just the height of the peak, it's the area underneath the peak. The relative sizes of the peak is called the integration, and the ratio between the sizes of the peaks is equal to the ratio between the number of hydrogens represented by each peak. Because a peak could represent just a CH, but it could represent a CH2, so it might represent two hydrogens. It might be a CH3. It might represent more hydrogens because you might have symmetry. So you might have two CH2s that are related to each other by symmetry, and therefore that signal will be worth 4 hydrogens. And then finally there's splitting. Splitting, unlike in carbon-13 NMR, which was kind of a separate experiment, splitting is always present, and splitting tells us how many hydrogens are on the next carbon over. Splitting patterns can be quite complex. We're going to start by focusing on the very simple singlet, doublet, triplet, quartet, and maybe come back at a later point to figure out more complex patterns. Now, the way I approach spectroscopy is by being systematic. I look at each thing in turn. If I had a formula, I would start with the formula. I'm almost always going to, in problems in class, we're always going to be given formula. If you didn't have it, you'd have to have other information that would give you the formula. But from the formula, I can figure out how many degrees of unsaturation I have, rings and or pi bonds. If I had the IR, I would look very quickly at it and figure out how many functional groups of various types that I have. If I had the carbon-13 NMR, I would count the signals, which would tell me about symmetry. I'd look at the chemical shift, which would tell me about the types of bonding. I'd look at splitting patterns, which would tell me how many hydrogens were attached to each carbon. If I had the proton NMR, I'd look at chemical shift, which tells me about bonding, integration, which tells me about how many hydrogens each signal represents, and splitting, which tells me how many hydrogens are next door to the hydrogen represented by that signal. These different spectra all tell me about the same molecule. And so today we're just focusing on, we're just going to focus on hydrogen NMR. But then we're going to, at a later point, go back and sort of put it all together and do problems where we've got some of each of these things. After I've looked at whatever spectra were provided to me, I would draw out the pieces. I know that I've got in a given molecule, a chlorine, a CH2, and a CH3. So I'd draw those out. I'd just write those things down. And then I look at those and I see, well, how can I attach a chlorine, a CH2, and a CH3? And it turns out that particular combination would only have one possible way of putting it together, because a chlorine makes one connection, a CH3 makes one connection because carbon makes 4 bonds, and a CH2 makes 2 connections because carbon makes 4 bonds, and therefore, the CH2 would go in the middle, and the chlorine and the CH3 would be attached to it, and that's 1-chloroethane. But even if I sometimes have multiple pieces, and when I put them together, there's more than one way to put them together. In either case, I would always go back and check my work. Again, be systematic, write things down. I generally just draw on the spectrum. I circle a signal and I say, oh, that's a CH3, or that's sp3 hybridized, or whatever. Be cognizant both of what's there and what's not there. And also start with the clear stuff and then go on to look at the unclear stuff. And really, the least clear stuff is always going to be the proton NMR splitting, or maybe I should say is almost always going to be the splitting patterns, the complex splitting patterns in proton NMR. So do those last if you have to, because oftentimes you don't have to get there. Oftentimes it's obvious once you've looked at all the other things, so you don't actually have to interpret all the information. So that's another piece of, that's something else I should have thrown in here. If I've got multiple spectra, I have more information, I almost always have more information than I need to figure out the structure. And so I don't necessarily have to interpret every little squiggle in the spectrum. As long as I come up with an answer and then I go back and look, it should be consistent with all of those squiggles. But I don't have to start out by, for instance, trying to look at the fingerprint region of the IR and see what that tells me. I wouldn't bother, for instance. Alright, so let's just start out with a practice problem here. C2H5Br. Yes, this one's obvious, hopefully, in that if you could draw out the Lewis structure just based on the formula, but let's look at the spectrum. When I am solving a spectral problem, if I've got a formula and a proton NMR, well, I'm going to start with the formula, and I'm going to see that this molecule has 0 degrees of unsaturation, because I can figure out the degrees of unsaturation as 2 plus twice the number of carbons, plus 1 times the number of nitrogens, plus 0 times the number of oxygens, minus 1 times the number of hydrogens, minus 1 times the number of halogens, all divided by 2. Or in this case, 2 plus twice the number of carbons is 4, minus the number of hydrogens, 5, minus the number of halogens, 1, is 0, divided by 2 is 0. So this molecule has no rings and no pi bonds. I then go on to look at the chemical shift, because here I've got a proton NMR. I'm going to look at chemical shift, and I notice that this is the region for hydrogens attached to sp3 hybridized carbons. So I'd say somewhere between 0 and 4-ish are hydrogens attached to sp3 hybridized carbons. Except of these two, this one's more to the left. And so it must be near something more electronegative. Well, in my formula, I have a bromine. So this guy must be near bromine, and this one not so much. Then I look at integration. Integration is usually going to be given as a value within parentheses. You might see these little S curves, for instance, in problems in an older text, for instance. But on a modern instrument, you'd also be given the values associated with the relative heights of those curves. In this case, it's 2 to 3. So I have a ratio of 2 versus 3 of the hydrogens due to this signal and the hydrogens due to that signal. I have a total of 5 hydrogens. So that means that this signal tells me about 2 hydrogens, and this signal tells me about 3 hydrogens. So essentially I have a CH2 and a CH3. Now, I should step aside and note that that's not necessarily true. Instead of having a CH2, I might have 2 identical CHs. And instead of having a CH3, I might have 3 identical, that is related by symmetry, CHs. But in this particular molecule, I've only got 2 carbons to work with. So it's not like I could have, 5 different CHs to account for. So be a little bit careful with that, but it's usually going to be pretty straightforward. If I integrate for 2, that's probably a CH2. There are some instances where that would be 2 identical CHs, and etc. And the last thing is splitting. Now, if I look at the splitting pattern, this signal is for a CH2, but the splitting tells me what it's next to. And here the splitting pattern is a quartet. And if we go back and go through our understanding of splitting, if I am adjacent to 3 little magnets, I will be split into a quartet. That is, if I am next door to a CH3. So the fact that this is a quartet tells me it's next door to 3 hydrogens. Notice this signal tells me about a CH3. It's split into a triplet. A triplet, well, we get a 3-peak pattern, a short, tall, short triplet pattern, when we're adjacent to 2 neighboring nuclear magnetic moments, which means when you're next door to a CH2, or 2 identical CHs. But in this case, notice we've got a CH2 that seems to be next to a CH3, and we have a CH3 that seems to be next to a CH2. That's pretty straightforward how these things are going to fit together. But let's draw out our pieces. We've already concluded that we have a CH2. We've concluded that we have a CH3. We know more than that. We know they're next to each other, but let's set that aside for... Well, sorry, I did make the slide do that. We know that they're next to each other because the CH2 is a triplet, which means, is a quartet, which means it's next to the CH3. The CH3 is a triplet, which means it's next to the CH2. So you put those together and you have an ethyl group, right? A CH2CH3. But that's not all my pieces, because if I look at my formula, I've got C2H5Br, and I've only accounted for 2 carbons and 5 hydrogens, which means I also need a bromine, but now this is really easy, because if I put these together, I get bromoethane. We should always go back and check ourselves. I have no degrees of unsaturation. Both of my sets of hydrogens are on sp3 hybridized carbons. One of those is closer to the bromine. There are CH2 and a CH3, and the CH2 is next to a CH3, and the CH3 is next to a CH2. By the way, that's always going to be true, right? Because if I am standing next to you, then you are standing next to me. And so they are going to have this kind of mutual effect. Of course, if we were in a line of 3 people, I'm standing next to you, and you're standing next to that other person. I'm standing next to you, but you are standing next to both me and that other person, right? So your pattern is going to be a little more complex. And that other person is standing next to you. And so when you've got kind of a chain, things in the middle of the chain might be more complex. Not true in this case. All right, let's do another example. C4H7Br02. Now this one's going to be a little harder. Here I've got a formula that, if I calculate it out, tells me, again, remember, 2 plus twice the number of carbons, plus 1 times the number of nitrogens, plus 0 times the number of oxygens, minus the number of hydrogens, minus the number of halogens. 2 plus 8 for the carbons, minus 7 for the hydrogens, minus 1 for the bromine, 0 for the oxygens. All divided by 2 is 1. 2 plus 8 is 10, minus 7 is 3, minus 1 is 2, plus 0 is still 2. All divided by 2 is 1. 2 divided by 2. This means I've got 1 ring or 1 pi bond. Also, if I have a pi bond, it might be a carbon-carbon pi bond, it might be a carbon-oxygen pi bond, just given the elements that I have available, right? I don't know which of those is true. I don't know, just from the degrees of unsaturation, I don't know if I've got a ring, I don't know if I've got an alkene, I don't know if I've got a carbonyl carbon, a CO double bond. If I had something like an IR, that might be very helpful. I don't in this case. I've just got this proton NMR. So let's look at the proton NMR. I see 3 signals here. They all seem to be on sp3 hydrogens on sp3 hybridized carbons. right? Hydrogens on sp3 hybridized carbons come between 0 and 4-ish. But of those, two of those signals, this signal and this signal, are more to the left. And they must be near something relatively electronegative. We got a couple of possibilities here. Bromine and oxygen, we don't know yet which it is. On the other hand, this signal seems to not be next to those, because it's more to the right within that sp3 hydrogen on sp3 hybridized carbon region. All right. What else do I know? Oh, integration. 2, 2, and 3. So the relative sizes of this signal versus this signal. I notice these are very different heights, but this one's essentially a very tall, very narrow triangle. This one is a shorter and fatter pattern of, it turns out to be 4 triangles. If I blow it up big, these are basically 4 triangles. It's a quartet. We'll get to splitting in just a moment. But 2, 2, and 3 adds up to 7. So I know that this one's worth 2 hydrogens, this one's worth 2 hydrogens, and this one's worth 3 hydrogens. That is, I seem to have a CH2, a CH2, and a CH3. Now, I should be careful. That's not necessarily true. Instead of having a CH2, I could have 2 related by symmetry CHs. Or instead of having a CH3, I could have 3 identical CHs. But we're going to start with the simplest assumption. Just keep in mind that we might have to go back and revise that assumption. But it would be easiest to think that we've got a CH2, a CH2, and a CH3. What else do I know? Well, this one just looks like a line. I didn't blow it up because it wouldn't show it. It would still just look like a really narrow, very tall triangle. This one's a singlet. But on the other hand here, I've taken this pattern. When you push it down into a small space, it's hard to see, but it's a quartet. It's, if I kind of expanded the x-axis, this here is showing me the pattern of what that looks like. It's a quartet. The same thing here. This one, if I kind of stretched it out, you would see that there's more pattern there. It's kind of shoved together there, but it's a triplet. So I got a singlet. That's not next door to any hydrogens. So my CH does not appear next to either this group or this group. But on the other hand, my CH2 seems to be next to a CH3. That's what it means to be a triplet. And my CH3 seems to be next to a CH2. That's a quartet. The CH2 seems to be next to a CH3. That's what it means to be a quartet. My CH3 seems to be next to a CH2. That's what it means to be a doublet. Right. Let's put our pieces together. So I wrote out all my stuff. I just label my spectrum and say, oh, this is this and this is this. Or you could do it, off to the side as notes or whatever. But it seems like I've got a CH2 that's kind of by itself, but I've got a CH2 and a CH3 that seem to go together. So those are those pieces. Are those all my pieces? Well, no. I've got a carbon that I haven't accounted for. I've got a bromine I haven't accounted for, and I've got 2 oxygens. So there's 4 more atoms to account. Now this is a little bit problematic. If I just drew out these, this makes 1 connection. So this seems to go on an end. And the bromine seems to go on an end. This makes 2 connections. That's somewhere in the middle of a chain. This makes 2 connections, 2 connections. And this makes 4 connections. 4 connections would make a branch. So it would seem like if it was like this, I'd have to... I don't have enough things to connect up here. Well, can I do this another way? How could I have a carbon that has no hydrogens? I could have connections to 4 different non-hydrogen things, like these other carbons and the oxygens, etc. Or I could have a CO double bond. Hey, that's going to help. Because if I do that, that'll account for my carbon. And now notice I've got 2 things that make 1 connection and 3 things that make 2 connections. And that's going to help because I got 2 things that go on the end, and then I got 3 things that connect in between them. Okay, those are my pieces. That's all the atoms in my formula. But I can string those pieces together in a variety of different ways. These are all 6 possible ways of putting together a 2-carbon piece, a CH3CH2 at one end of the chain, and a bromine at the other end of the chain. And in between, I've got a CO double bond, a CH2, and an O in just different varieties. Okay, I got 6 possibilities here. So the Tinker Toy step, basically just thinking of those as pieces and sticking them together in all possible ways, leads to a lot of different possible arrangements. Well, let's go back and check ourselves. How can we eliminate things? All of these seem to have 1 degree of unsaturation, the CO double bond. I crossed out these 2 down here. What's wrong with those? Well, one of the things I knew was that my CH2 and my CH3 were by each other, but they were not by this CH2. This was a singlet. And notice, if it was either one of these, I'd have a CH3, a CH2, and a CH2 that were in a chain. The CH3 would be a triplet. This CH2 would be a triplet because it's next door to this. And then this would be a very complex pattern because it's next door to 3 hydrogens on that side and 2 hydrogens on that side. So at least in theory, you could see a 12-peak pattern because you would see a triplet of quartets or a quartet of triplets. In practice, those would tend to be more messy looking because they overlap. In either case, we see a clean quartet, a clean singlet, and a clean triplet. Can't be these. Now that would be consistent with any one of these 4, right? So we have to start looking at things in a little more detail. I see that my CH3 is not next to anything strongly electronegative element, but both of my CH2s are. If I look at my different possibilities, we'll see that in this case, both of my CH2s are by oxygen. In this case, one's by oxygen and one's by bromine. But in this case, not so much, right? They're like a couple of atoms away from something electronegative. Now this is where we start getting into a little bit of judgment calls, because remember I said I don't want you to learn, a whole bunch of specific numbers. I'd rather you learn trends. But if things are at the far left side of this region, they're probably directly next to something electronegative. So that's going to allow us to cancel out those top 2 cases. And now we're going to have to get even a little more into a judgment call. We got 2 possibilities left. They're both pretty good answers. If this was an exam question, for instance, and you gave me the incorrect one, well, you'd still get most of the credit because you've got the good wrong answer, as it were. But let's look at these. In both cases, I've got an ethoxy, and so that seems very consistent with this and this. This guy, this CH2, well, it's either in this molecule or this molecule. In this molecule, it's between a bromine and a carbonyl. In this molecule, it's next to an oxygen and a carbonyl. If it was this molecule, I would expect it to be even more to the left. Because notice that this CH2 is only by an oxygen. Oxygen is the second most electronegative element. That shifts it quite a lot. If something was both by oxygen and, next to a carbonyl, which has a partially positive carbon, which is going to start shifting things, I would expect it to be even more shifted. So if it was this, I would expect this signal to be even more to the left. So on the other hand, I'm going to go with this. I'm going to suggest that this is the best answer, and that this one doesn't quite fit. If you had said this one, I would respect that answer. I would give that most of the credit. If it was like a question that was worth, 10 points or something, you'd get, 9 or something like that. There's a reason why this is the right answer and that's not right. But this is, certainly at this stage of the game, when you're just starting to learn spectroscopy, is a pretty good answer. You might look at this further and say that some things seem odd about this structure, like this functional group is one you've not seen. You haven't seen it where there's a CO double bond with a bromine directly connected. You might have some chemical intuition that you haven't seen that before, that's probably because that sort of thing would be quite unstable. That's true. That's a pretty good reasoning as well, whereas this thing seems more in keeping with some of the things that we know about the stability of different structures. But that might be a little bit advanced right at this stage of the game. So like I said, either of these is a pretty good answer, but this one turns out to be best. If it was this, I really would expect this particular singlet to be more like 4.7 or maybe even almost 5. I don't know exactly where it would be. I'd have to look. Also, if it was this, it would be a much less stable molecule, and that would be a bit of a giveaway as well. If we had other spectra, like IR or NMR or carbon-13 NMR, that would also be helpful, because an ester functional group, that carbon in the carbon-13 NMR turns out to come at a slightly different place than an acid halide, which is this functional group. Also in the IR, a CO double bond stretch is a little bit different for an ester versus an acid halide. But that's probably beyond the scope at this stage of the game. But if we're systematic and we go through our spectra and we label everything and we see how that can fit together and we look at all the possible combinations to fit that together and eliminate the ones that can't work, we're going to end up with either the right answer or something that's pretty darn close to the right answer every time, or maybe I should say we're either going to end up with the right answer or a judgment call between two things that would give similar spectra, and we'll be able to get pretty close to the right answer, even given sort of our level of experience at this stage. As you become more experienced, you'll become even more adept at this. You could also turn to tables and look things up and figure out where exactly the signals would come in each of these cases, but again, that would be fairly advanced because you'd have to look at a bunch of different tables to figure out where exactly this sort of signal would come and where exactly this sort of signal would come. All right, that's proton NMR. We're going to go on and talk about other types of spectral data, and then do some practice putting it all together in combined spectral problems. So I look forward to talking to you again in the future. Thank you. Bye.